Good morning, everybody.
Good morning.
All right. Hello, everybody. Hope you're doing well. It's Thursday morning. So hopefully you all saw that I posted the information about the project on Moodle. So let me go through that now so that you all have a better idea of what the project is. All right. So if you go onto the Moodle page and scroll down, will be this, the generator project. So what is that, the third, fourth thing down there? So the way that this project is structured is that there are 4 PDF documents here. So this first one, let's take a look. This is the intro and describes the entire scope of the project. And these other 3 are guidelines and grading rubrics for the 3 separate parts of the project. Okay. All right. So are you all seeing this PDF now? Yeah. Okay. So the project, call it the Junkyard generator project, because the idea is to use like free or scrap materials if possible to create a generator. So this is an application of Faraday's law where you will build something where you either do some kind of crank or movement or some sort of human power that translates that human power into enough voltage to turn on a LED light. So we just on Tuesday, right, we began discussing Faraday's law, and we saw that there's 2 ways, right, that we can take either the movement, change in the movement of a loop of wires or set of wires, or we could take change in the magnetic field, and either one of those we can use to induce a current and a voltage on a set of wires. So this project is an application of Faraday's law, right? In Faraday's law, you need either the magnetic field to change or the wires to change in order to make that voltage. So this project is an application of Faraday's law. So in this project, you can either choose, I don't mind, you can either have a single person or 2-person teams. So normally I would do 2-person, but if we were all in person together, but since, some people, like in this case, I think maybe Cade, you may be the only one in Idaho Falls, and some of you, I think maybe like AK, you mentioned you lived in Blackfoot, so it may be a lot more convenient for you to actually work by yourself, right? Since just because of various constraints. So if you regularly meet with someone else or want to, or that's your choice. So you can either do single or 2-person teams. I don't mind either way. And the rules are that you should try to make this from free materials if possible. But if you can't use just free materials, then you should spend less than $20. Okay. So you should spend less than $20 if you do end up buying stuff. Okay. So you can use anything you want, just, know that, it might break or whatever, right? And then don't do anything that's, too dangerous either. And then I am going to ask for a budget, right? So if you do end up spending money, then show that you spent less than $20. And also there is a section of the grading that's a bonus. And so there will be, one way to get that bonus would be to have the least expensive project. So the idea, right, is not to go out and spend a lot of money on this. You can use anything that you want to figure this out. Okay, so you can talk to people, you can look up videos on YouTube, search the web, whatever you choose, you can do that. But in the end, you need to design and build and test this by yourself. So you need to actually build it yourself. Okay. And then you can also discuss your approach with your other teammates. But another way to get the bonus points is creative design. So if you have a very creative design, right, you might not want to share that with anyone else until the end when we have a presentation. All right. And then one more major rule is that any of the windings that you do, right? So in that problem that we worked on Tuesday, right, we saw there's like a coil of wires that had N loops. So most likely you're going to make something that has a coil of wires. And the reason, right, that you will do that is because we saw that flux phi and the VEMF are related, right? So the VEMF is equal to minus N times d phi dt. So that minus N modifies that d phi dt, the flux, as it changes in time. So if that N is higher, then that's going to make your voltage higher. So you're probably going to have a bunch of windings. And when you have those windings, that you need to make those windings by yourself. So no using prefabricated motors or windings. And if you don't know what those look like, basically, if you purchase one of these, then this is like a prefabricated winding. Okay, so do the windings on your own. All right, and the generator, it should be human powered, and it should create enough light to turn on a small LED or some other bulb of your choice. So I'll leave it up to you, but as a hint, I think, do any of you know which LED color requires the least voltage to turn on?
The white one.
Yeah, that may be true. Do you know what that is? How much voltage it is? Let's check. I actually can't remember. I was thinking that it might be, yeah, okay, so white, this one is actually going to be probably pretty hard, 3 to 5 volts. I think that red is 0.7. Yes, 1.7 to 2. So it all depends. but do keep in mind that some of these are different, right? And so, you know, if you might have some in your, kit or something already, but just keep in mind that some LEDs do have different voltages that require the turn on. And so if you are, so like this says, typical is 1.8 to 3, red is 1.7 to 2, but blue is 3 to 3.3. So if just giving this example, right, all else being the same, you would potentially need 2 times the amount of windings to turn on a blue LED, right? So that's a pretty big difference potentially in your project. So choose something that has a reasonable voltage that you want to turn on. That's one piece of advice from me for you. Okay, you can, whichever way you choose, right? You could produce either AC or DC. So if it's AC, you might have a light that's flashing off and on. That's fine, as long as you can see that it's turning off and on. So no using batteries or capacitors or other energy storage devices. If you can show me that you're using a capacitor to smooth like a AC rectifier, I would be okay with that. But obviously, you're going to need to show me that you built that rectifier circuit or something, or what your approach was there, and make it pretty clear. And then, please avoid injuries. If you're doing something dangerous, wear eyeglasses. Okay, any questions about the rules? All right. So grading. All right, so this full project combined is 15% of the final grade. So it's like a little bit less than an exam total. So the full thing is worth about 15%, or the full thing is worth 15%. And then these are the 3 sub items that you'll be doing that are worth various percentages of that 15%. Okay, so there's going to be a progress meeting, video, and a written report. And these 3 items, these 3 things that you will turn in, will comprise the totality of the grade for the generator project, which is worth 15% overall. So for the project, the first deliverable, right, is this prototype meeting. Okay, so this is going to be in the week after the Thanksgiving break. All right, on that Tuesday. So in class, we'll schedule times where each team is going to meet with me for 10 or 15 minutes and show me the progress that you've made on the project. Okay, so this is something new that I added this year, and the idea is just to make sure that you are working towards completing the project. All right, so it's just to add in a little bit of accountability. Then so that's 10% of the project grade, and then 60% of the project grade comes from the video demonstration that you will make. Okay, so this is the presentation. All right, so the presentation has 4 different sections. First is showing that you met the guidelines, which includes turning on the LED. The second is demonstrating the junkiness and creativity, right? So showing a budget, showing that you spent as little or no amount of money, and also how creative your design is. Then another 15% is understanding. So in this one, you're going to explain the physics behind this. So you'll describe the workings of your generator using the first principles. And then the next 15% is just the overall demonstration and explanation video. Okay. So you will upload this video. You can either upload an MP4 to Moodle, or you could upload to YouTube, and then I will collect all of those and make them available to the class so that everyone can view the other generator projects and see how everyone else did. And in the written report, the last part, which is 30% of that total grade, you can you'll be asked to write up your design, and also within that report you will need to do some analysis of another team's design so that you can just write about what other ideas you got from the other teams and what other teams did that you could implement on your own project if you were to continue it. As I mentioned, there is a possible 5% bonus that you can get. So that could be for a number of different things. Okay, so if you can measure the voltage that yours is generating, right? Whoever can generate the maximum amount of voltage, that would be one bonus that I would give. Another bonus I would give would be for very creative designs. Another one that I've been waiting to see is that you should be able to integrate a Ferrite core into your design, which I have not seen anyone do yet. So I'm curious to see someone try this at some point. So that could be pretty simple, possibly as simple as just wrapping your windings around a bolt or something that has a lot of iron in it. I'm not really sure. So that's another potential bonus that I'm curious to see. So this is how all of the grading will work. So does anyone have any questions about the grading? Yeah. So each one of these grades, I have a little bit more detail in a separate document, and we'll look at those in a moment. But before we go on, I want to show you the suggested timeline. All right. So today, this is Thursday during week 9. So right now you're receiving the instructions. So I would suggest that you begin to think about and research this project. Think about what scrap items you might already have, what you might need, where you might get them from. And then maybe over the weekend or early next week, I suggest that you start researching and designing the generator and seeing what you might need. And during this week, I highly suggest that before the end of next week, if you are going to purchase something, I highly suggest that you purchase it. Okay. So it might take a while for the items to arrive, and you need to account for those shipping delays. So if you need to purchase something, I would suggest doing it next week. All right, then spend week 11, 12, and 13. Right, I would suggest you basically finish your design, build it, iterate the design as needed, right, to make any improvements, and then possibly begin writing the presentation and report if you get that far. And then week 14, if you need to, of course, work on it during the fall break for Thanksgiving. But if not, I just set that week aside. And then week 15, after the Thanksgiving break, on Tuesday, there will be no normal class on Tuesday. And instead, I will schedule meetings for each individual team. So I will give you a time to come to class. So and we'll discuss that later, but let's say, I'll just give you a window. So for example, maybe Calvin is 8 to 8:10, then Daniel 8:10 to 8:20, something like that. I'll give you a time slot that week, and we won't have normal class on Tuesday. We'll just you'll have a 10 to 15 minute meeting during that class to show me your project and the progress that you've made. And then during this week, and the next week, you will prepare a final video. It doesn't need to be like really high production value or anything, but you'll need to cover a few items that I'll show you in the other paper. And so this is due, the final video presentation is due before Thursday, December 9th. And this is basically the last normal class period. Okay. So this is the Thursday before the finals week. And then the written report is due on the Monday of finals week at, just before midnight. Okay. Questions? All right. So each one of these describes in more detail what you should do for the deliverable. Okay, so the first deliverable, right, is this progress meeting. And so in the progress meeting, it's worth 10% of the project grade, and we'll have a 10 to 15 minute meeting. And during this, what I want you to do is show me your designs or plans for the generator. I want you to show me that you have the items that you're using to build the generator. Okay. I want you to show me a draft of the budget that you used. And then I also want you to show me your preliminary calculations and estimates for the EMF voltage that you're going to generate. All right, so this is what will be in the meeting. So basically, by the time we have this meeting, so after Thanksgiving, you don't necessarily need something working per se, but I want you to have the plans. I want you to have the things that you're going to use in hand. I want you to have the budget, and I want you to have a start on the calculations that you are going to do. Then the generator video is due on that Thursday at 9 before class. So just record it. It should be a MP4 file, and you can upload a MP4 direct to Moodle, or you could, Moodle it's not that great for uploading things to. So I would suggest that the YouTube uploader is a lot better, and it's easier to upload to YouTube and then send me a link. But if you don't feel like doing that, that's fine. And if you also don't want your video to be, searchable on YouTube, just choose the unlisted option. The unlisted video option makes it so that the link can be shared. So like you could give me the link or other people the link, but you can't search for it in the YouTube. So use whatever you have to record it, or you could use multiple things, but laptop, cell phone, other cameras. If you're having trouble, we'll figure something out, but I think all of you have a webcam on your laptop, and if not, you probably have one on your cell phone that you can use. But let me know at least a week in advance if you're having trouble getting access to a camera. And your video should show a good demonstration of the project. So especially when you're turning on the light, right, I should be able to see you holding the project, turning on, cranking it, or whatever mechanical motion you're using to turn on that light. And the video, it should only be 5 to 10 minutes, and it would contain the following things: introduction, explanation of your design process, show me that you're using junk and hand winding, so there's no pre-purchased motors, and a project budget. You'll explain to me how your generator works and the underlying physics, and you should give me some estimate, some analytical estimate for your VEMF voltage. Okay, so this will basically, right, you remember we were using that equation on Tuesday, right, where we had the we had the VEMF, and we were looking at like number of windings, the loop size, the B field. So I want you to estimate, do some kind of analytical estimate for your EMF voltage. Then demonstrate that it turns on. And then if you have anything else unique or any kind of bonus that you're going for, make your case for it. So show the peak voltage, show me what's unique. etc. All right. And so this is 60% of the project grade. So I'm going to grade it out of 60 points. All right. So each one of these sections is worth 5 points. Questions on this part? Okay. All right. And then the last and final part is the written report. So the written report is 30% of the project grade. So you will submit this. Oops, this is wrong. I will update this. So the correct time is was given here. So it's due during finals week on the same day as our final. So it's just due that evening. Use 12-point font, 1-inch margins. Use the IEEE style. You can use single column or double column, whichever you prefer. Your report should cover the following sections. You should have an introduction, a design process, explanation of your analytical estimates based on the theory, budget, and then a section on design improvement. So in this section, you will want to write about what you learned from the other team's designs. All right, so this is the only section that you can write everything from here up. You could write this by the time that you submit the video report, but you only have 4 or 5 days to finish this section. So you'll be able to, so after Tuesday, I will post all the videos and you'll have some time to look at everyone else's video and write this final section where you're just writing what you learned from the other team's designs and how you could use that to improve your own design. And this is how I'll grade each part of the written report. Okay. So this section on basically following basic formatting, and then some more points on basically that you have tried to make a readable report, right? You've used you used the spell check, right? You made your verb tenses agree. Okay. So basically just, did you make a report that's easy for me to read? And then the other ones are related to covering the coverage of these sections. So that is the full explanation of the report. Sounds like so far there's no questions. Maybe we've covered everything now. Does this bring up any questions for you? Okay, well, I think the only other hints that I want to give are still related to the materials, which is, you know, be sure to, if you need to order wire or magnets, those are probably the main things that you might need to find somewhere, right? You might have some of these, you might happen to have some powerful magnets randomly and a bunch of wire, you may or may not, right? But if you do need those things, consider looking for those right away, especially if you're buying them from Amazon or something. I just last year there was someone who purchased some magnets and it took some super long amount of time for those magnets to arrive, and so I don't want that to happen to you. And I think there's also going to be a lot of shipping delays this year. I don't know if you follow that information in the news, but that there's likely to be a lot of delays in shipping, especially approaching the Christmas holiday. And then the other thing that I want to mention is, right, the wires, right? You can choose whichever gauge of wire that you want, but there is, some gauges of wire may work better or worse. So consider that as you're making your wire. So I'll leave it up to you to think about what the difference in the wire is, or which wire you want to choose. But the main difference that I can explain to you is this: smaller gauge wire has higher internal resistance, which leads to less voltage, but you can pack more loops into a given space using a smaller gauge wire. Okay, so the larger gauge wire has less internal resistance, but it's harder to pack it into tightly wound loops. So that's the trade-off between larger and smaller wires. I would definitely say don't get too large of wire. Okay. You may also want to consider with wire, some wire comes with a coating on it, right? A thin, like it looks like copper, but it actually has a thin coating on it, right? That's good because you can tightly wrap those wires together without any shorting of the wire. But if you choose like, jumper wires, let's see. These ones, right, they probably have this type of wire has quite a bit of coating around it, right? And it has a lot of plastic coating around it. So that might be harder to wrap closely together. Okay. And then with magnets, right, there are different types of magnets. So I'll leave it up to you to choose ones that you think are the strongest and to choose ones that have a field shape that you think is suitable. So those are my advice. I do think that maybe Home Depot has magnets as a local place. Okay, so there are a decent amount of magnets that you could buy that are in stock at Home Depot. If you wanted to go buy some somewhere in person. And then of course, Amazon and possibly other places have magnets. If that's something that you need to purchase. All right, questions? Thoughts? Anyone already have an idea of what they're going to make? Cade, you have an idea? For some reason, I actually cannot hear you. I don't know why. Can other people hear Cade?
No, I can't hear him.
Can you hear me now?
Yes, I can.
Okay. Yeah, I built something, but I haven't tested it and I haven't done the wire
Okay, cool.
winding.
Yeah. So, yeah, sounds like some of you already have some ideas. Hopefully have some cool ones. Again, my purpose for this project is that, traditionally an electromagnetics course might have a laboratory component, but this class does not. So instead I implemented the project. So hopefully you have some fun with it. I want to give you a lot of leeway to do whatever you want in terms of creativity. And then hopefully too, I think you can maybe guess, but right, you can, without even going too crazy, there's some very simple designs that could be done that would fulfill this project. And then of course there's a lot of other complicated ones that are pretty cool that would also fulfill it and possibly make a lot more voltage. So if you want to get some inspiration to some things that you might look for, I mean, obviously if you just start searching YouTube for generators, you'll find some. But if you look up like windmills or homemade windmills, those might give you some ideas of some ways that people make generators of their own that have a lot of tightly wound loops or a lot of magnets. So and there's you can get pretty complex with this and come up with some pretty interesting geometries that will increase the voltage by using clever designs. And then don't forget too, right, that there's two ways that you can make EMF voltage. One is to move the magnetic field, to make a time-changing magnetic field. The other is to make a time-changing loop, so movement in the loop. And then a third way is to combine both of those together. So have a changing magnetic field and a changing loop in time. So many ways to do this. All right. So I think I've said plenty on that. If you do have any questions, just let me know and we can talk more about it. I'm guessing too, after you have a weekend or to think about it, that may spur some more questions as well. All right, so let's look at the homework. So I think we finished A, B, and C on this problem on Tuesday. And then let's just take a look at that last part of it here quickly. So we want to find the induced current in that circuit. And I don't think we got that far last time. Okay. So I think we finished by looking at the polarity. And we had determined that the voltage was, let's see here. So we had an expression for voltage. And it was what? Oh, omega t. Does this look right? That's what y'all had.
Yeah.
All right. So if we want to find the induced current in the circuit, we look at VEMF at time equals 0, which if this is 0, right, this cosine should turn to 1. So we would have 188.5 volts, and right, this was the negative polarity. So that means that the voltage was actually opposite of how we defined it at this moment in time. So now, and that's actually how it's drawn here, right? The voltage or the current must go from high to low. And because it's negative, right, we're actually going from high to low. So let's rewrite this as a little circuit. Okay, and we can write it in either way, but right, let's write it this way, where we have this is 188, this is negative 188.5. Okay, but our voltage or current is going in that direction. So what is going to be the current at time 0? How do we find that?
We just divide the voltage by 1K ohm.
Yep. Yeah. So right, this is not that complicated for this case. right? So this should be yep. Does this look right? 188. And then we could write this expression anytime, right? So that for any time it would be this. Okay, so we can also find a time varying expression for the current, or we could find the current at a specific time. All right, so that's the last part of this problem. And that problem was all doing transformer EMF. So there's a few other problems in this. Okay. So let's look at, I don't know, what do you all want to look at? Problem 2, 3, 4. I think 4, let's look at it at the end maybe. So problem 2 or problem 3?
We do problem 3.
Okay, sounds good. So where to go? All right, so problem 3. We have a rectangular loop that has a constant width. And so that is this measurement here, all right? This is constant. But the length, this one is changing with time. As this bar, right, this is a conducting bar, slides across these rails with a uniform velocity. In this case, the magnetic field is static. Okay, so the magnetic field, right, this is pointed at us and it's not changing in time, right? So this magnetic field is not changing in time, but it is changing in distance, okay? All right, the bar starts at x equals 0 at time 0. And we want to find the EMF between terminal 1 and terminal 2. Okay. And we also want to find the current that goes through the resistor. In this problem, we're going to assume that the resistance of the wire is very, very small. So the wire from here to here, we're assuming has almost no resistance. And this is the main resistance. So if we can get information about the emotional or the electromotive force, are we going to have any transformer EMF for this problem?
No.
Yeah, and why do you say that?
We need windings for it.
Not
I don't know.
necessarily. So the main way we can differentiate these is the transformer EMF comes from a time varying magnetic field, and the motional EMF comes from a time varying movement of the wires. Okay, So you can have windings with a moving B field and get a transformer EMF, or you could have a loop of windings that you're spinning around in time and you could get motional EMF. So there's a couple different ways. Those are the difference between the transformer and the motional EMF. Okay, so we're going to say that this one is 0 and that all of this EMF is motional EMF. Okay, so that does for us open up two different ways that we could approach this problem. Okay, so those two ways. So no matter what, so this is always the case. So we can always write that the EMF can be found this way. So this is always true. And we could even rewrite this as by substituting the integral expression. So this is always true. This is always how you can find EMF. But there's another way for motional only. That you can find the VEMF, which is by taking the motion crossed with the magnetic field. And so U cross B, is this a vector or a scalar?
A vector.
Yep, this one's a vector. And so then if we take this vector value and cross it with a line, what is this going to be? So this dot with the line DL, will this be a vector or a scalar overall?
Should be a scalar.
Yep, yeah, that's correct. So this is the other approach, is to first get the vector, get this vector describing the cross of the motion in the field, and then dotting it with a line integral or a path that you're taking to get a vector value. So we can always use this, and we can also use this one. Okay. So which way would you like to see this problem solved? Method 1 or method 2?
Method 2.
Yeah, let's look at method 2 then. And don't worry, in the solutions, I've written the solution both ways. So in the solution later, you can go and look at my solution on how to do it that way. Okay, so let's look at method 2. And in this one, right, we're going to look at solving this. All right, so in order to evaluate this, and this should be a closed loop, in the end. Okay, so the full EMF, we should look at a closed loop on this. All right, so what do we know? Do we know what this is? Yes, no, maybe.
We know the direction.
Yeah, we know the direction. So this one, we aren't quite sure. So we'll have to come back to this. What about the B field? Do we know this?
Yes, we do.
Yeah, we know this one. And what about DL? Do we know what this is going to be? So if we want to take a full path around this, we're going to have to choose a few different DLs in order to make it convenient. So we're probably going to want to look at this. This is kind of hard to see. Let me choose a different color. I'll make it big. So we're going to want to look at these different paths. So some of these, right, some of these paths, if I move on this path, what's changing? X, Y, or Z?
X.
Yeah, so this one is a DX path. What about this one?
Y.
Yeah, and this one's a Y path. So we'll just keep that in mind now. So we'll loop back to this, but this one could be, this one could be either, depending on where we're at. All right, so looking at this, we have the bar and it's moving. And the bar is moving. What direction is the bar moving in? So what direction is this vector in? Yeah, it is in the X direction. And do we know anything else about the bar movement? Don't think so. So let's just say, we don't know what it is, but let's just say that the velocity is u, okay? So the velocity is u. So we don't know what that number is, but we'll just call it u. So that's the velocity that it's in. And it's uniform, right? It's not changing. So u is not a function of time. So the uniform velocity means it's not a function of time. All right, so I think we have enough to get started on this now. So the first thing that we should find is u cross with b. And b is 0. All right, so what is this going to be? Take a minute and solve this and then let me know. Once you have it, just shout it out. Let me know what you got for the u cross b.
minus y at v naught x u.
Yes, right? So that looks correct to me. So for the x, right, we have this minus this, which is equal to 0. And then for the y, right, we have, then for the y, we got it, that one's different, right? Because we have that plus minus rule. So we have this minus this. That's where this negative comes from. So that's correct. And then for z, right, we're back, we have this cross this. So z is equal to 0. So that cross product is minus y hat b naught x u. All right, so we now have a result for this. So let's go and let's make a note of that. Okay, so now that we have this, now we know the direction of this. We also can say this. All right, so now let's go back, and we made a note that we're going to come back to this DL. So let's look at DL. So from 1 to 2, from 1 to 2, the DL is, oops. So is this cross with this DL, is that going to give us anything?
No.
Yeah, it's not going to give us anything, right? Because y dot with x, it doesn't give any value. So that leaves us with the fact that only some of these are going to actually give us any value on this, okay? And what we can also see is that if we do a full loop around this, we will come back around to, I think we should come back around to 0 potential. So looking at this loop, we can see that the potential on this one is actually going to be the same as the potential across this, right? So the voltage from here to here should be the same as the voltage from here to here. So that leaves us with this one as being the easiest probably to solve for, since it's just this straight line. Okay. So that one, this path goes from, was that 4 to 3 or 3 to 4, depending on how you want to say it. So from 3 to 4, we have the DL is equal to y hat dy. And what should our integration limits be for this? Well, we aren't really sure, right? But we called this 0. So let's say that this point right here, let's call this, let's just say this is the entire origin of the coordinate system. So if this is y equals 0 here, what is y equal to at this point?
Would it just be L?
Yep, yeah. We know that the bar is length of L. Like this. All right, so what is, take a minute and see if you can come up with a solution for this VEMF. So take the dot product, do the integral, evaluate the integral. All right, anyone get an answer?
Minus B naught X U L.
Yep, this looks correct to me. Anyone else get that?
Yeah, I got that as well.
Okay, perfect. All right. Now, the one last thing to realize is that this distance that's been traveled for any given amount of time, we could travel a distance x naught. And so distance, right, is equal to velocity multiplied by time. So we could substitute this. We could also write this as this, where this is substitute. Just using that simple relationship that we learned in physics to get a expression that is time dependent. Okay. So this is the final result for an expression for the EMF voltage. As a function of time. All right, so whenever we use this U cross B method, typically we're going to end up having some sections of the integral that don't actually add, okay? And that's almost always going to come from the velocity crossed with the magnetic field is going to give us some directional component. And what we should realize is that only the DL that is in the same direction is going to contribute to the total voltage. And then the other thing that we will want to realize when we're solving it these ways is that usually, right, the two of the segments, if you have a Cartesian system like this, two of the segments will have equal but opposite voltages across them. And so you may, in order to find the voltage, you are only going to need to solve for one of those in a lot of the cases. Okay. Does that make sense?
Yeah,
Okay.
it does.
And then the other thing that we're going to see is this is kind of a weird way to make a changing loop of wire, right? Like by sliding something. By far the easiest method is going to be some variation on this theme, right? Let's say we have a loop of wire. Like this. Okay. The easiest way to do that, to rotate this, is to put it on like a stick or something, right? And then to rotate this angularly. So from above, that might look like this is like a loop. And it's rotating in a circle, right? So this is some kind of rotation. So we'll look more at this later, but rotating something on its axis where you have a constant B field is another common way, right? So as this loop changes, as the loop moves through this, right, there's going to be different amounts of B inside of the loop, which is going to mean that a magnetic field is changing inside of a loop of constant size, which is another really common way of getting motional EMF. And that motion we'll see is usually like given as omega t. So the angular velocity is a common thing that you would need to know in some of these later problems. Okay, so let's look at one more problem. Oops. That's based on the Lenz's law. Okay, so if you have two loops of wire that are very close together, and the switch in the bottom of the loop is closed at time 0 and then opened at a later time, we want to find the direction of the current in the top loop at each of the two times. Okay. So this is an application of Lenz's law where we're assuming that this section, right, these sections of wires are very, very long and close together. And so they'll be coupled to each other. Okay. So what happens when you close this at time is equal to 0? So let's draw the circuit at time 0 plus. What direction is the current at time 0 plus?
Clockwise.
Clockwise? Like this?
Yes.
Okay, perfect. So then on this, so then we have two things. Okay, so if the current is clockwise here, then is the field, so we have loop 1 and loop 2, and is the field going into the page or out of the page in this loop 1? Into the page or out of the page?
Into the page.
Yeah, so if we put our hand on there like this, we can see that it's into the page. What about in this loop?
Yeah.
And it's coming out of the page on this side. Questions about that? Does this make sense to everyone?
Yes.
Okay. So is this current, so right at time equals 0, right when it's closed, is it increasing or decreasing? So right after you close that switch, what's happening? Is it increasing or decreasing? I'm sorry, what was that?
Increasing.
Yeah, it's increasing. And why is it increasing? How do you know?
Because we have more current flowing through.
Yeah, and what was the amount of current flowing through at time 0? So before you close the switch is open. What is I?
0.
Yep. And then at I at t equals 0 plus, it is I. So it is increasing, right? So it is getting bigger. All right. So what, in order to oppose that increase, so this is B is increasing on that. So what is the B? Oops. So what is the B induced going to be for this top loop? What would oppose? So if this B is increasing and it's increasing out of the page, what would be the induced magnetic field that opposes that change? So how do you oppose this magnetic field that's increasing? Let's think of the direction. So is a magnetic field that's opposing B, so is the induced magnetic field, is that into the page or out of the page?
Induced one will be into because it has to like negate it, right?
Yep. Yeah. So induced field, here, I'll put it right here. An induced field is going to oppose that change. So there's going to be a field into the page that's induced that opposes that the B. Okay. So we have this B due to the current in loop 1, and there's going to be an induced magnetic field that's into the page that opposes the magnetic field that was out of the page due to this current. All right, so if that happens, what is the direction of the current in loop 2? So what is the direction of current due to this induced magnetic field? Clockwise or counterclockwise?
Clockwise.
Yeah, so again, we use our right hand rule. Our fingers are pointed into the page and our finger is in this direction. Our thumb is in that direction, giving us a clockwise. Okay, who has questions about this? You feel like you can do the opposite case? So at time, so if this is loop 1, this is loop 2. Okay, so what is I at time equals T1? So the switch is closed in loop 1. What is the current? So what's the current at time t equals 1? At T1. It's just a current, right? We don't know what it is, but it's some current. What about at time equals 1 plus? So this is at T1. What happens at this time? What's the current now?
0.
Yeah, it's 0 now. So what happened to the magnetic field there? And what was the direction here? And what happened? Yeah, I guess let's start by this. So the current was still in this direction, right? Which led to us having the field look like this, right, along this axis. So when you open this, does that field, what happens to the field? Increase or decrease?
Decrease.
Yeah, decreases. And the current becomes 0. Okay. So we had a field that was into the page here and out of the page here. Right, so this decreases rapidly. So how do you oppose this decrease? So it's pointed out of the page at us, but it's decreasing. How do you oppose that decrease?
You move in the same direction to increase the magnet.
Yep, exactly. So to oppose it, so it's out of the page, but getting smaller. So to oppose it getting smaller, there's an induced field that's in the same direction, right? So it's getting smaller and there's a new field that gets induced that's trying to keep things in that direction. Okay, so I'll leave it up to you to figure out what the current direction is later. Sorry, I went a couple minutes over time, but this is how to apply Lenz's law in a qualitative manner. So thank you for sticking around for the extra minute and feel free to take off. If you have any questions about the project or anything else, just stick around and I'll answer your questions.
Thank you.
Yep.
Dr. Kreisler, you said we'll do the quiz.
Yeah. Yeah. So I'll send that to you in just a moment here. So AK, do you have any questions?
Yeah, I just wanted to see when it's best time to meet with you or something over
Yeah.
Zoom or something like that.
That sounds good. Let's see here. Are you free today?
Yeah, most likely I'll be free. But I have a class from 12 to 1:30 or something like that.
Okay. Let me all right. Okay, so Daniel, I'm gonna send you the quiz here and you have the 20 minutes to complete it. And then AK, I will send you a Zoom invite in just a moment here, and we can go into that Zoom meeting and discuss any of your questions. Does that work?
Yeah, sounds great. Thank you.
All right.
And should I email it back to you or should I just put it?
Yeah, just email it back to me. Yeah. All right, and I will send that to you in just a moment. All right, and yeah, once you get it, you'll have 20 minutes. So I'll send that to you. Actually, well, hang on here, and I'll